Hello everyone. So this is a question from JEE Advanced 2025 paper 2. Monocyclic compounds. So monocyclic means those compounds which contain exactly one ring. So we have P, Q, R and S are the major products formed in the reaction sequence given below. Okay. So they have given us some compounds and some sequences they have given, and then we have to predict what is P. Same thing, we have to say we have to find out what is Q, we have to find out what is R, we have to find out what is S. Product having the highest number of unsaturated carbon atoms is. Okay. So we need to know what is the meaning of unsaturated also. Unsaturated carbon means the carbon which is attached to a double or a triple bond. Okay. So they're asking us to find in PQRS which one will have the maximum number of carbon which is attached to double or triple bonds. Okay. So the chapters involved is aldehydes, ketones and carboxylic acid, hydrocarbons and general organic chemistry. Okay. So in P, the starting compound is a carboxylic acid, right? So this is the starting compound in the case of P. Okay. And carboxylic acids, except formic acid, which don't contain an alkyl group, they will react with chlorine or bromine in presence of small quantities of red phosphorus and H2O to give exclusively alpha chloro, or you can say alpha bromo acids. Okay, so that is when we have a carboxylic acid. So except formic acid, they will react with Cl2 or Br2, also in presence of red phosphorus and also water, to give exclusively alpha chloro or alpha bromo acids. Okay, so and also one more thing, this reaction is also known as Hell-Vollard-Zelinsky reaction. It's a famous name reaction. Okay, HVZ reaction. Okay, and this is then what's the meaning of alpha chloro or alpha bromo acids? The meaning is, the in carboxylic acids that we have taken initially, the carboxylic acid that we have taken initially, in those, the alpha hydrogens will be replaced by, if you are reacting with chlorine, it will be replaced by a chlorine atom. If you are reacting the carboxylic acid with bromine, one of the alpha hydrogens will be replaced by bromine. So that's the meaning of alpha chloro or alpha bromo acids. Okay, so I'll give you an example. Let's say I have RCH HCOOH. So this is, let's say, a carboxylic acid having alpha hydrogen. So this is the alpha carbon and this is alpha hydrogen. So we are reacting this with, let's say X2, which can be, chlorine or bromine in the presence of red phosphorus. And the second reagent we have taken is water. So what will happen, instead of, this X will be replaced by, depending upon what halogen you have taken. Okay, so we will be getting RCH XCOOH. So these guys are known as alpha chloro or alpha bromo acids. Okay, so in our case, in the case of P, the starting compound is this, and yeah, so this is the starting compound. I'm writing the alpha hydrogen out, and we are reacting this with, first Br2 red phosphorus and second water. So what is going to happen, this H will be replaced by a bromine. So ultimately the P will be CH2CH So this is P. Okay, and let's count the number of unsaturated carbon atoms in P. So this is 1, 2, 3, 4, 5, 6, and this is the 7th. So there are total 7 unsaturated carbon atoms in P. Okay, so total 7 unsaturated carbons in P. Cool. Okay, so then if you go and look at Q, the starting compounds of Q, so we have, aldehydes, both are aldehyde, and we have aqueous NaOH as the reagent. So this makes it very clear that, the reaction is going to be aldol condensation. Okay, so in Q the starting compounds are two different aldehydes, and this is benzaldehyde, this is acetaldehyde. Okay, so I will write it down for our understanding that we have started with benzaldehyde and acetaldehyde. Cool. So as you can see, this guy is benzaldehyde. This does not contain any alpha hydrogen. Okay, but this guy is acetaldehyde, so this has alpha hydrogen, right? So therefore two products are possible. First is self aldol product of acetaldehyde, and so let's do that first. So to find out the self aldol product of acetaldehyde, so we take two molecules, since there will be plenty of them. So let us take two such molecules of acetaldehyde, CH3CHO, and let's write the other one in this way, CH3CHO. Okay, because this aldol reaction is based on the attack of alpha hydrogen, so I'm writing it in this fashion. So obviously alpha hydrogens are acidic, so they will bear a positive charge, this guy will bear a negative charge. This is the carbonyl oxygen negative, this is the positive, and we can send them to their opposite charges. So this happens in the presence of aqueous NaOH of also 293 Kelvin as given in the question. So we will be getting CH3COH. So there is CH obviously. This is connected to CH2CHO. So what happened exactly is this H became a part of this O, and this leftover group, this became a part of this C, and this is the final product that we got, right? Cool. So this is the first product that is possible. The second product is, as you can see, we have benzaldehyde which does not contain alpha hydrogen. We have we have acetaldehyde which contains alpha hydrogen. So this guy can undergo self aldol, so we got one product. Now this guy can also attack benzaldehyde, so we'll get the another product will be cross aldol product of acetaldehyde on benzaldehyde. Okay, cross aldol product of acetaldehyde on benzaldehyde. Okay, so to do that, what we do is we write them in this fashion. We have a benzene, we have benzaldehyde, and we have acetaldehyde which contains the alpha hydrogen. So I will write it in this fashion. Alpha hydrogen, again they are positively charged, the rest of the molecule negative. Carbonyl carbon positive, carbonyl oxygen negative. So what's gonna happen, this H is gonna react with this O, this rest of the molecule is gonna get attached here. So again under the conditions of aqueous NaOH and 293 Kelvin, so what's going to happen, this H will become a part of this O, and the rest of the molecule will become a part of this C. So we will get benzene ring CH OH CH2 CHO. Okay, and one more thing is this reaction won't stop here. Okay, so this reaction will itself lose a molecule of water, that is undergo dehydration. Okay, so the initial formed aldol, this is the aldol which has been formed, undergoes dehydration to form an alpha beta carbonyl compound. Very important. So this aldol undergoes dehydration to form an alpha beta carbonyl compound. Okay, to understand this, what we have to do is, and let's understand the reason first. So why is it happening? The driving force for this dehydration is the conjugation of the double bond with benzene ring and carbonyl group. Okay, so I will draw the figure, you will understand. So let us say that I can write this CH2 in this way, CH and CHO, right? And during dehydration, OH from here and H from here goes out in the form of water. So after dehydration, we get this benzene ring, CH double bond CH, C double bond OH. So this is what we get after dehydration. Okay, so can you see there is conjugation double, single, double, single, double. That's why, it is automatically losing water to give us a alpha beta carbonyl compound. Okay, why? Because this is alpha carbon, this is a beta carbon, and in these positions there is a double bond. That's why this is known as alpha beta, and also it contains a carbonyl group, so that's why it is known as alpha beta carbonyl group. Okay, so, or carbonyl compound. So the driving force is the conjugation, extensive conjugation. Okay, so this is Q, this is the product Q. Okay, and it has a name, it is also known as cinnamaldehyde. Okay, and this is obviously the major product, because can you see there is conjugation in this system, double, single, and double. So there is conjugation, extensive conjugation, but this is also formed, but this won't be the major product, because here we don't have any conjugation. Okay, so therefore obviously this will be Q, and let us count the number of unsaturated carbons. So obviously 1 2 3 4 5 6 7 8 9. So there are 9 unsaturated carbons on Q. Okay, 9 unsaturated carbons are present on Q. Cool. Then we have to find out what is R. Okay, so, and it is something like this. We have a benzene ring, we have a carbon which is triply bonded to another carbon. Okay, and we have certain reagents, that is NaNH2 and haloalkene, then mercury ion and hydronium ion, and we have to find out what is R. Okay, so you can see, to find out R, the starting compound is an alkene, sorry, it's an alkyne, and it's a terminal alkyne, to be honest. Okay, and hydrogen atoms which are attached to the triple bond of alkynes are very, very acidic. Okay, so this is an important point, that is hydrogen atoms attached to triple bond of alkynes are acidic. Okay, so this H is very, very acidic. Okay, so therefore these terminal alkynes, they react with sodamide, NaNH2 is sodamide, to form the corresponding acetylids. Okay, therefore this alkyne will react with sodamide, that is NaNH2, and we will get the acetylide, that is C triple bond C minus and Na plus. So these are known as sodium acetylides. Okay, and yeah, and when we treat this sodium alkanides, okay, these are also known as alkanides, so haloalkenes. So can you see, the next step is, after we have got the acetylides or the alkanides, we treat them with haloalkene. This is a haloalkene. So whenever treated with sodium alkanides, haloalkenes form higher alkynes. So I will write down this statement. When treated with sodium alkanides, haloalkenes, in our case it is CH2 double bond CH, CH2 Br, or you can write it like this also. Okay, so it forms higher alkynes. Okay, so the meaning of higher alkynes is, obviously it will have more number of carbon atoms than we started with. So let's say here we have X, so obviously the ultimate alkyne that we get will have more number of carbon atoms. Okay, so how will this reaction proceed? So obviously we have the haloalkene, it is CH2 double bond CH, CH2 Br, and we have the alkanide, that is Na plus, that is this guy. Okay, this guy is reacting with you can see this guy, first it reacted with sodamide, so we got this guy, and this will react again with this haloalkene. Okay, So this is reacting with Na plus C minus triple bond C, then benzene ring. Cool. So what is going to happen? We will lose a molecule of NaBr, okay, and we will get this alkyne, that will have a benzene ring. I will have C triple bonded to C, then that is connected to CH2, then CH, then doubly bonded to CH2. Okay, so this is what I will be getting, and you can see clearly this is a higher alkyne because it contains more number of carbon atoms than I started with. Okay, cool. And can you see the next reagent is Hg plus 2 and H3O plus, that is mercury ion is present. Okay, and alkynes in presence of HgSO4 or Hg plus 2 as catalyst, hydration occurs readily. Okay, so this is an important point, that alkynes in presence of HgSO4, or sometimes they just simply mention Hg plus 2 as catalyst, what's going to happen? Hydration occurs. Cool. So H2O adds to the triple bond, that's what is hydration, and it follows according to Markovnikov's rule. Okay, so H2O adds to the triple bond according to Markovnikov's rule. Okay, important. I hope everyone knows what is Markovnikov rule. So I will give you the statement, that is negative part of reagent goes to carbon atom of multiple bond which carries lesser number of hydrogen atoms. Okay, so I will write down the statement, that is negative part of reagent goes to carbon atom of multiple bond, that is can be double or triple, which carries lesser number of hydrogen atoms. Okay, so hydration occurs, H2O adds to the triple bond according to Markovnikov's rule. Okay, and they form an enol. Okay, so hydration occurs, then they form an enol to form enol. Okay, what is a enol? Enol is an organic compound containing a OH group attached to a carbon atom that is part of a C double bond C or a double bond. Okay, so I will write down enol is, this name has come from en plus ol. So this means a organic compound that contains a OH group attached to a carbon, to a C double bond C, to a carbon which is a part of a C double bond C bond. Okay, and so what is happening, we added, in the presence of Hg plus 2, alkynes will add water to form enol, and that enol will readily undergo tautomerization to form the corresponding carbonyl compound. Okay, so and enol readily undergoes tautomerization. So we'll see what is the meaning of this term, tautomerization, to form the corresponding carbonyl compound. Okay, so the journey in a nutshell is, so we have alkyne plus H2O hydration in the presence of Hg plus 2, we will get enol. That enol will undergo tautomerization to give us the keto form, or you can say we'll have the carbonyl compounds as our final answer. So it can be a ketone, it can be a aldehyde, depends. Okay, so this word, that is tautomerization, so tautomerization also has many types. In this current situation, we are talking about enol and keto, that is keto enol tautomerism. So in this tautomerism, what happens is hydrogen migrates from one polyvalent atom to third polyvalent atom. Okay, this is the catch. in this keto-enol tautomerism, hydrogen migrates from one polyvalent, that is having more than one valency, atom to third polyvalent atom, and it is within the same molecule. So this migration is within the same molecule, and tautomerization is a special kind of functional isomerism in which the isomers exist in dynamic equilibrium. Can you see, this is the sign that I have drawn when I wrote tautomerism, because the one form of tautomerism, that is enol form, is in dynamic equilibrium with the keto form. So it is the only type of isomerism which involves dynamic equilibrium. So these isomers are in equilibrium with each other. Obviously one will be more stable, another one will be less stable, right? So we'll see that in a while. So okay, so we have an alkyne. Okay, remember yes, this is the alkyne that we got. So I will write this guy again. This is important. So this is my alkyne. Okay, and this is the guy with which I react, Hg plus 2 and H3O plus, right? So I am writing 1 and 2, focusing on the carbon atoms which is triply bonded. So there are two products possible. We'll get a mixture of product. Okay, why? Because obviously we are adding water, isn't it? That is hydration, so which is basically addition of OH minus and H plus. So this OH minus can either attack on the first carbon, or this OH minus can either attack on the second carbon. Both the attacks are possible. Okay, so let's say first case, that is when OH is, or you can say when OH attacks, when OH minus attacks C1. Okay, so then what's going to happen? Let's show the arrow like this. So then what will happen? Obviously then H will attack the second carbon, so we will get benzene ring, we will get COH, we will get a double bond, then H attached to this, then CH2, then CH, then double bond CH2, right? So this is the enol form. Can you see? Because this carbon is doubly bonded to another carbon, and to this doubly bonded carbon we have a OH. That's why it is known as ene plus all enol. So this guy will undergo tautomerization. Okay, so now you will understand what is tautomerization. So I will write tautomerization. So I gave you the definition of tautomerization. This is especially keto-enol tautomerization. Hydrogen migrates from one polyvalent atom to third polyvalent atom. So can you see, here we have a hydrogen. Let's say this is the first polyvalent atom, second and third, right? So we have a hydrogen here also. So I will write it down again, 1, 2, 3. So this H will migrate to this carbon, or you can say 1, 2, 3 to understand it better. This H goes to the third polyvalent atom, and this pi bond shift here. So ultimately after tautomerization we'll be getting benzene ring, C double bond O. So I will show this shift, and C H H CH2 CH double bond CH2. Okay, so this is, let's say, 1. It is also possible that this guy OH minus attacks C2, and this H plus goes and attacks your C1. That will give us the next product. Okay, so if in that case, so let us say when OH minus attacks C2, okay, in that case we will get benzene ring, CH double bond COH CH2 CH double bond CH2, right? Now again this is enol. Can you see? C double bond C, and OH is attached to a C double bond, a doubly bonded carbon, right? Cool. Now again let's say this is 1, 2, 3. So migration of H from one polyvalent atom to the third. So this H will migrate to this carbon, and this pi bond will become a part of this. This pi bond will result into the carbonyl CO, C double bond O. So I will show the migrations like this. So therefore, after tautomerization, so doubly bonded arrow because they are in dynamic equilibrium, right? So tautomerization, I will get benzene ring CH, C double bond O, CH2, CH double bond CH2. Cool. And so therefore, let's say this is 2. Between 1 and 2, if you remember the question to find out, R, they have said that you have to take the major product. So between 1 and 2, okay, 1 is the major product, okay, and the reason is due to conjugation. Can you see double, single, double? There is conjugation in this system. There is no such conjugation. Double, single, single. There is no such conjugation. So therefore, this is the major product, okay, and that's why this is our R. This is R. And let's calculate the number of unsaturated carbons that it contains. 1, 2, 3, 4, 5, 6, 7. 1 second. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are total 9 unsaturated carbons. Okay. So that's the story of R. Then let's talk about S. Cool. So in S we have a benzene ring, which is 1 second. So we have, I will draw the structure. We have ozone, zinc, dust with water. Second, we have a Grignard reagent, 2 equivalents. And third, we have H plus and heat. Okay, cool. So in S, to find out S, can you see the starting compound has a benzene ring. This is the benzene ring fused with another ring. This is one more ring, right? So benzene undergoes, so can you see here we have ozone. So this benzene undergoes ozonolysis, yes, but in this case, the double bond from the next ring, that is this bond, undergoes ozonolysis because if we maintain aromaticity, the product that we'll get will be very stable. So that's why, instead of these 3 bonds undergoing ozonolysis, this one will prefer to undergo ozonolysis. Okay. So regarding ozonolysis, whenever, ozone is passed through an alkene, okay, whenever we have ozone passed through alkene, it oxidizes the alkene to ozonite. So we convert the alkene to ozonites, okay, and these ozonites are reduced with zinc dust. So we reduce them with zinc dust to give aldehyde or ketone or a mixture of these. So we can either get aldehyde or ketone or their mixture. So it depends upon the structure of the alkene, okay. And so let us start with our starting compound, that is this benzene ring and this double bond. So obviously it will react with ozone. To get the ozonite, what we do is we don't write this is the double bond, right? So we simply don't write the double bond, okay. Remove the double bond, forget about the double bond. So I will write it in this fashion. So this carbon, so you can write it like this, C, it is attached to one more CH3, and this carbon will have a CH. Yeah, so simply write it in this fashion and connect them to oxygen. This is the ozonite. So this guy is the ozonite of this, after breaking this double bond of this alkene. This is the ozonite, okay? Then next what happens is, obviously we are reacting it with zinc and in the presence of water. So what will this zinc do? This will get this oxygen. This zinc will get this oxygen and it will lead to, the destruction of this ozonide. So look at these arrows carefully. Okay, so ultimately we will get can you see here we have a C. This CO will, due to the breaking of the ozonide, this will convert into a ketone because this is connected to one carbon, this is connected to one more carbon, so we'll get a ketone here. So therefore C double bond O CH3. In this case, do you see here we have C, which is connected to one more carbon, and it is connected to one oxygen, so which will get converted into O, C double bond O. So here we will get an aldehyde. H, yes. So this is what we are going to get. Okay, then we are reacting next with Grignard reagent, very important. So Grignard reagent react with aldehyde and ketone to form alcohols in 2 steps. First step involves nucleophilic attack of Grignard reagent to carbonyl group to form an adduct. Okay, so Grignard reagent plus aldehyde ketones, 2 steps. First step is nucleophilic attack of Grignard reagent to carbonyl group to form adduct. Second step is hydrolysis of the adduct with water or acid to form an alcohol. Hydrolysis of adduct with water or acid to form an alcohol. Okay, so in the option, can you see we have been given with 2 equivalents of Grignard reagent? Why? Because we have got a ketone as well as a aldehyde. So one of them will each react with an alcohol, to give us 2 alcohols. Okay, so to show that, so what we will do is we have obviously the intermediate CH2, C double bond O CH3, and we have C double bond O H, right? So when they react with Grignard reagent CH3 MgBr, there are 2 equivalents, so I will write them twice, CH3 MgBr. Now look at the signs, plus minus, plus minus, and carbonyl oxygen negative, positive, negative, positive. So what's going to happen? This MgBr will come and connect with this O. This CH3 will come and connect with this C. Same thing here, this MgBr will connect with this O. This CH3 will connect with this C. Okay, so we will get the adduct, and the adduct will look like this. Benzene ring, CH2, CO, MgBr, CH3, CH3. Cool. Then we have C, O, MgBr, CH obviously, and CH3. So this is what we are going to get, right? Cool, this is the adduct. And then obviously the next step will be the hydrolysis of the adduct with water or acid. So we have acid in the third sequence. Can you see we have acid available to us? So then we will do hydrolysis using acid. So this will result in the formation of this OMG-Br group into an alcohol. So we will ultimately get benzene ring, CH2, COH, CH3, CH3, and CHOH, CH3. And obviously, MgBrOH is the side product, 2 moles of them. Now, this has not ended here, because can you see there is a symbol of heat? Very important. Okay, alcohols when heated in presence of H plus around 160 degrees Celsius to 170 degrees Celsius, they undergo intramolecular dehydration to form alkenes. Okay, so in general, so let us say we have alcohols CH COH. So these guys, whenever we have H plus and heat, so H plus will be available in plenty. So they will, first this OH, O has a lone pair, this will give its lone pair to this H plus. So it will form a OH2 plus ion. And this oxygen, since it has its electronegative, it bears a positive charge, so it will take this electron pair with itself. So therefore we'll get a carbocation, CHC plus. And therefore it's important that you look after for rearrangement in these kind of reactions, okay, because carbocations can undergo rearrangement to become something even more stable. And then what will happen, these sigma bonds, they will become pi bond. Ultimately we will get alkene. So we will get C double bond C, and obviously water out, right? So in our case we have this intermediate, right? This is what we have got, CH2C OH CH3 CH3, and we have CH OH and CH3. In the presence of H plus and heat, what will happen? This OH will react with this. There will be plenty of them. So this OH will also react with this H plus to form, benzene ring, CH2, COH2 plus, CH3, CH3, CHOH2 plus, CH3, right? Now, again, as oxygen have positive charge here, and also oxygen has positive charge here, so they will take away this electron pair, resulting in the formation of carbocation, okay? So look at these arrows. So we will get benzene ring, CH2, C positive charge, CH3, CH3, and CH positive charge, CH3, okay? Now can you see there is a rearrangement possible? Here it is not possible. Here it is possible. A hydrogen can shift there and the positive charge will shift here. So this will result in the formation of a allylic carbocation next to a double bond, which is a part of an aromatic system. And allylic are more stable because of resonance. So this shift is possible. So because of shift, we will get benzene ring, CH positive charge, CH, CH3, CH3. So I will write this CH in this fashion, okay? Yes, and here it will remain as it is, CH3, because a carbocation on benzene ring is not that stable, okay? Now I will write this CH3 in this fashion, CH2H. Now what is going to happen? Obviously, this H will form, this sigma bond will form a pi bond. This sigma electrons will form a pi bond here, and it will result into the respective alkenes. So we will ultimately get benzene ring, CH double bond C, CH3, CH3, and CH double bond CH2. So this is the ultimate product, that is S, and obviously H plus will be out and regenerated since it was the catalyst. So can you see here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 unsaturated carbons here. So therefore S will have the highest number of unsaturated carbons. So therefore S will be the answer. I will mark them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so therefore S will be the answer. Thank you.